Hello, welcome to my channel. Welcome to Rehendran. In this video, I'm gonna talk about RL circuit with a DC source. What happens when a DC source is applied to when a DC source is applied to a RL circuit, and we are gonna see the behavior of the circuit. Okay. We are gonna see the behavior of the RL circuit when a DC source is applied. Uh, Now let's go to the video. Now let me draw the basic circuit. So when the source is present, RL circuit, the series RL circuit is this. So say the DC value is Vs plus minus is R, this is L. So at first we're gonna do the time domain analysis. Okay, so time domain analysis. So to get the behavior of the circuit, let us assume the inductor has initial current IO equals I minus I plus. Now the RL circuit is an LTI system, and as it is an LTI system, it abides by superposition principle. That's why we can apply KVL KCL. So and after applying KVL KCL, it will generate differential equation. So after applying KVL KCL, it will generate linear differential equation with constant coefficients. So say loop current IT, for loop current IT, R I plus L D dt I equals to Vs. When the RL circuit was source free, there was no e- extra source voltage or current. Okay, that's why the equation was R I plus L di by dt equals 0. But in this case, there's a source, a DC source, so R I plus L di by dt equals Vs, the magnitude of the DC. So let me rearrange this. It will give R plus L and d by dt. Let us replace it by linear differential operator d. It will give I is function of time and Vs. Now this is a linear differential equation with constant coefficients. The constants being R and L are constants. Okay. Now, as this is a differential equation, it will have the solutions in two parts. One is complementary part and the other is particular integral part. For complementary solution, which will give us the transient response of the circuit. Transient response is the response of the circuit when there's no source uh, connected to it. Okay, when there's no source connected to it. And the particular integral is the response of a circuit when or response of a system. Okay, so particular integral is present in a electrical system when there's source connected to this electrical system. Okay, so now for the complementary complementary solution, the characteristic equation the of of this system. Okay, a characteristic equation of the LTI system is R plus LD equals 0. This whole expression is called the characteristic equation, and it will give us the values which are known as characteristic values, or also known as the eigenvalues. Okay, so it will give us D equals minus R by L. This is the eigenvalue or characteristic value of the whole LTI system, and it will give us the transient response of the system. So for transient response, we will get uh, the complementary solutions are always in. So if you didn't know, the complementary solution to a differential equation are always of the form y yt equals c1 e to the power lambda 1 t plus the others. Okay, this is the basic uh, solution. So where c1 is an arbitrary constant and lambda is the eigenvalue, the here in this case the eigenvalue lambda 1 is minus r by l. So the solution is it equals c1 to the power minus r by l t. So for particular integral, it equals vs by uh, r plus ld equals vs by l into d plus r by l. So which will give us e to the power minus r by lt by l to the power r by lt vs by d. After applying a formula, we get this expression. Now 1 by d is an integration. Okay, so it will give us to the power minus r by lt and e to the power r by lt vs, and this is l and this is l by r. So it will cut out the L part of the circuit and give us, and this will also vanish. So the L will vanish, the exponential part will also vanish, leaving behind Vs by R, and thus this is the solution. It equals Vs by R. Now at this point we have found all our responses. The full response is it equals I transient part plus IPI part. Okay, the whole response gives C1 e to the power minus R by LT plus Vs by R. Okay, now all we have to do is find the arbitrary constant. We know that initial current through inductor L at t equals 0 is the DC value IO, so which will give I0 equals C1 e to the power 0 plus Vs by R, thus giving IO equals C1 plus Vs by R, which gives C1 equals to IO minus Vs by R. See complete solution of the LTI system RL. IT equals IO minus Vs by R e to the power minus R by LT plus Vs by R. This is the transient part. This is the particular integral part. Also, in terms of frequency response, this is called the natural response and this is called forced response. So the thus complete response in TDA, in time domain analysis. Okay, in TDA. So as we know, the RL circuit is an LTI system. Due to its linearity, due to the linearity of the system, we can transform it into frequency domain. Okay, so with the help of Laplace transform, we will get the transform circuit plus minus Vs by S. R is frequency independent, so it will be the same, it will remain the same, but L with initial voltage, but inductor with initial voltage, if we use the voltage analogy, so it will give minus plus this. Okay, this will be SL L I O. Okay, so now in frequency domain analysis, the same applying KVL IS. Okay, so R I S plus S L I S minus L I O equals Vs by S. Obviously, S is the transformation of the unit step function. In the Laplace transform of unit step function gives us Laplace transform of unit step function gives us 1 by S. Okay, now by rearranging R plus SL IS equals vs by s minus plus lio. The linear transformation of the LTI system has made the equation generated by the system an algebraic one. Okay, so is equals vs by s into r plus sl plus lio by r plus sl. It will um, automatically, it will directly give us the answer. Okay, so vs by s into s plus r by l, with l as common and out taking l outside. Now io s plus r by l will vanish out here in this case. Now all we do is take out the Laplace transform. Okay, so here we have to do a partial fraction. So say it's a plus s plus b by s plus r by l, 1 by l plus io by s plus r by l. Now let us get the value of a and b, so which will give us 1 equals a s plus r by l plus bs. Let s equals minus r by l, which will give us 1 equals minus r by l b equals minus l by r. And if we equate the coefficient of s, it will give a plus b equals 0, which will give us a equals l by r. Now if we, so we got b equals minus l by r, a equals l by r. So now if we substitute the value of this, we get l by r s plus minus l by r s plus r by l, 1 by l plus io s plus r by l. Okay, which will give us, if we take the common, r by l by r will give us 1 by s minus 1 by s plus r by l, 1 by r. Okay, l will cut each other out, io s plus r by l. Now if we just inverse Laplace transform these, which will give um, here by inverse Laplace transform, is will become it, and this will become 1 by inverse Laplace transform 1 by s will give us the value 1 minus e to the power minus r by lt plus io e to the power minus r by lt. Oh, we have here vs. Okay, so it will be vs. Okay, let me write this cleanly. So we so here vs. So vs is commoned out, and we get 1 minus e to the power minus r by l t, vs by r obviously, and plus io e to the power minus r by l t, which is the full response of the circuit. Okay, if we rearrange this, it will obviously give io minus vs by r e to the power minus r by lt plus vs by r. Thus, in frequency domain, the circuit response is the same. Okay, is the same as we found in time domain analysis. Okay, this is the transient period. No, this is the transient part of the circuit, and this is the particle integral part of the circuit. The transient response dies out, and only remains the particle integral part. Okay, so far we found that in time domain analysis, the answer to the circuit response is io minus vs by r e to the power minus r by lt plus vs by r. In frequency domain analysis, we also get the same expression, io minus is by r e to the power minus r by lt plus vs by r, where this is the transient term. The transient term of the circuit of an LTI system dies out with time. Okay, and leaves behind only the particle integral part. The particle integral part is the forced response of the circuit. Okay, thus the answer in both time domain and frequency domain analysis. And that's it for today. In the next video, I will talk about RC response to DC value. And if you have any problem in understanding my explanation, you can write in the comment section. I'm trying to solve the circuits and upload the videos as soon as possible. And if you like this video, please like, comment, share, and subscribe to my channel. Please support me, and that's it for today. Thank you.